Okay.
One in the class except for like band.
Back to evaluating limits. So today we're going to look at some analytical approaches. Last time we just looked at properties of limits. Today we're going to kind of look at how do we algebraically deal with type 1 limits. Because remember what we said last Friday. We said that if you try direct evaluation or direct substitution, one of three things is going to happen. Either you're going to get an answer, right? You're going to get something you get an answer with no zero on the bottom, and you're done. That's the value of the limit. You might get an answer that looks like a non-zero number divided by zero, which does not exist, and we'll go further with that soon. Or you might get an indeterminate form. You might get something that looks like 0 divided by 0, or later in the year, something like infinity divided by infinity. What does that mean? It means more work, but how? So we've got to resolve that indeterminacy. The third type of answer ultimately is going to be resolved into one of the first two. Either we're going to get a numerical answer and their limit exists, or we might find out it doesn't exist. Okay? So what about, let's start off with something pretty easy. X squared divided by x. What does that simplify to? X, right? You can cancel an x in the top and the bottom. So my question is, our original function, x squared divided by x, the same thing as what we end up getting, our simplified result, x. If we call the first one on the left side of the equation f of x, and what's on the right side g of x, are they the same? They're not. They're not the same.
Their answers are 0.
Okay, there you go. So they are almost the same, but they're not. In the first case, f of x, there's one really important feature of that. Are there any values of x that we must restrict from the domain?
0.
Yeah, okay, so in the blue case, x cannot equal 0. Now in the red case, that's not a problem, right? 0 is in the domain of the red function. That one little difference is really key, okay? Because what that allows us to do then, if we are trying to take the limit of that function, by canceling the x's on the top and the bottom, I sometimes call those the offending factors, because those are the factors that cause this thing to be indeterminate. The fact that we had x's on the top and the bottom, if we are trying to do something, and let me state what we're trying to do here, I guess. We're trying to take a limit, first of all. I want to make that blue. We're trying to take a limit of this function, x squared divided by x, as x approaches 0. Well, if I try to evaluate that directly, what do I get?
0 over 0.
0 over 0, right? 0 over 0 means more work. That's our indeterminate form, right? Okay, what's the more work in this case? What do you think?
Simplify to the other equation and value of that.
Yeah, we're going to simplify that. We are going to cancel the factor x from the top and the bottom, and this is going to become instead the limit of the red function as x approaches 0. And what is that answer if I evaluate directly? It's 0. Yeah, how about that? So we know the answer. Now we can see that from the graph. As x approaches 0, what y value do we think we're approaching? 0, okay? But now we got there algebraically. We didn't have to use the graph. Okay, what's the secret there? How come that worked? By canceling the offending factors of f of x, we fill in the hole, essentially. We generate a new function that's literally exactly the same as the original one at every point except one. It fills in the hole in the original function, which allows us to take the limit directly. Now let's think about this in terms of our conversation about limits from last week. As x approaches 0, if we're taking a limit, does x ever actually get to 0? It doesn't, right? Remember, that's the behavior of a limit. That's the nature of a limit. X approaches but never gets to 0. So we're just trying to figure out what value does the ant anticipate stepping on. Okay, that doesn't really help us very much with the blue form of the function, because we end up with the ant anticipating stepping on a place that looks like 0 divided by 0, which doesn't tell us anything. That's indeterminate, right? Okay, but by trading the blue function for the red function, it gets really easy for us to determine where the ant thinks he's going to step. On the red function, as x approaches 0, the ant believes he's going to step on that one point right there, which is a part of the function. Everybody see that? So in the red case, the ant actually would step where he anticipates stepping. He would end up where he thinks he's going to end up. In the blue case, he would not, because there's no place to stand. Well, what's an easier case to deal with? The red case or the blue case? The red case. Isn't it easier to answer the question, where does the ant think he's going to step, by just plugging in a value and finding out where he actually would step? Which we can do for any function that's defined at the value of x we're approaching, right? So our strategy is to resolve the indeterminacy is to literally trade the original function for a new function that agrees with the original in all places except one, which is that it fills in the hole. Okay? So that's the theory behind it. And let's just read through this and make sure this makes sense. By canceling the offending factors of f of x, we fill in the hole and generate a new function g of x, whose limit you can easily find using direct substitution. This function shares the same limit as the original function, the blue one. So we've also found the limit of the original function. We've just done it in a way that's a little bit easier, okay?
And will that always be like simplifying the original function?
It
into
will,
another one?
it will, yes. Anytime those factors cancel, that's going to resolve the indeterminacy, okay? So, the limit of f of x as x approaches 0 is the limit of x squared over x as x approaches 0, which simplifies to the limit of x as x approaches 0, which is 0 in this case, right? To find the limit of a function at a hole, all we have to do is find a function that agrees with this function at all points except the location of the hole, the one that fills it in, okay? And evaluate that function instead. So in practice, this ends up being pretty simple. And it doesn't even have to, it applies even in situations that, like with piecewise functions. Let's look at this example. If f of x is defined as this piecewise function, f of x is equal to the quadratic function x squared plus x plus 1 for all values of x not 1. So every place where x is not equal to 1, that's the function the ant is going to be walking on. At the one value of x equal to 1, we assign the output value of 1, right? So that's kind of a bizarre behavior. The ant's going to be walking on this parabola. If the ant were to actually step on an x value of 1, he gets beamed down to that single point. And then if he takes another step to the right, he's beamed back up onto the original parabola, right? Kind of bizarre, piecewise behavior. Okay, if I want to find the limit of f of x, I don't want to write the whole thing down. F of x is that piecewise function. As x approaches 1, could I define a simpler function that agrees with the blue function every place except at 1? What would it be?
Yeah, that first quadratic.
It's just going to be that first quadratic, right? Right. So that's equal to the limit of x squared plus x plus 1 as x approaches 1. Because they share the same limit, right? Here's the red function. Don't they share the same limit? As x is approaching 1 on the blue function, where does the ant anticipate stepping? Right there, right? He anticipates stepping on a place that's actually a hole. But again, the limit doesn't care with what happens when he gets to 1. The value of the limit is 3, isn't it? We can see it graphically. Everybody agree? Give me thumbs on that, up, down, sideways. Does that make sense?
Why is the limit not 1?
Why is this limit not 1? Because remember, the limit, in the limit you never actually get to x equals 1. It's all about where do you anticipate stepping, right? So as the ant approaches 1, the ant anticipates stepping on a y value of 3. So that is the limit. It's irrelevant that when he gets there, he ends up someplace else, because the limit is not concerned with the actual behavior at that point, only as you approach that point, right? Where does the ant anticipate stepping on the red function? Same place. But the red function is easy to evaluate because this is the case where the ant steps where he thinks he's going to step, and that's an easy question to answer. Where does he step? He steps at the point 1 squared plus 1 plus 1 equals 3 if I evaluate that directly. That's a great trick.
What's the difference between the red and the green and the blue? Is it just because it's not equal to 1?
Yes, the
Okay.
blue function, the value, in the blue function, f of 1 is equal to 1. In the red function, we'll call this g of x, g of 1 equals 3. Well, that's a lot better for us to use to evaluate a limit, right? Because it's continuous. The ant steps where he thinks he's going to step. And the question of where he actually steps is what you've been doing for years. That's just evaluating a function. Okay? See the trick? So it even applies in weird situations where we don't even really do any algebra, right? But we did, in a sense, because we just traded the original function for one that fills in the hole, which is easier to evaluate. Okay, what does this look like? And there's just kind of what we just did for the notes. Okay, how about one like this? If I want to evaluate, and again, we'll say the first one is, here, let me color code these. So here's our blue function. Here's our red function. It's not red. That's red. Oh, it's still not red. That's red. And we'll just make that a point. We don't need to. Okay. So the limit of the red function is indeterminate, right? As x approaches 1. Indeterminate. Okay. So how do I get to the red function using algebra? Exactly. Remember, there was a trick there. I have to cancel the offending factor. Well, what factor?
X minus 1 from 1, so we can divide out.
There you go, right? So you already can anticipate what's going to happen here. You know that if I factor the polynomial on the top, you already know what has to cancel. To fill in the hole, what has to cancel is the factor x minus 1, because that's what's causing the indeterminacy, right? And that's what's causing the 0 over 0. So you already know that this is going to look like the limit of x minus 1 times something else on the top divided by x minus 1 on the bottom. And by canceling these out, I'm going to get rid of that 0 over 0 nature, right? And I'm going to end up with a new function whose limit is easy to calculate. Okay. Well, how do we factor the top? I'll give you a hint. X cubed minus 1 cubed. How do we factor a difference of cubes? It's been a while.
There's some shortcut you can take, I just don't remember it.
Remember how that works? Well, let's just remind ourselves about
I
that.
think that we're gonna get an x squared plus an x plus 1 maybe.
A cubed minus b cubed factors into
Great question.
a minus b times
A plus B.
Where?
a squared plus
B.
AB.
ab
Oh,
plus b squared.
Can we just like get a sheet with all those on it?
Yeah, actually you can. And actually what we will do here soon is we'll do a little memorization quiz to help you guys, help encourage you to just, and is, okay, now, you've heard me say this many times in the past, that memorizing things is kind of a low-level skill, but it's essential, because you don't want to interrupt your train of thought. So in order to be able to do algebra quickly and efficiently, you don't want your brain to have to pause and think about the factoring part. You want to be thinking about the overall strategy instead, right? Because that's what calculus is all about, is coming up with strategies for solving problems. Okay, so then the top factors into x minus 1 times
Squared plus x plus 1.
x squared plus x times 1, which is x, plus 1 squared, which is 1, right? Make sense? Okay, and look what happens. Yeah, look, the x minus 1's cancel, and now we end up with a limit that we can evaluate. And what's the answer as x approaches 1? 3. Hey, what do you know? That's my answer, 3. Okay? So what, if we break this down to kind of just like the nitty-gritty of doing the algebra to resolve the indeterminacy, how are we thinking about that? Well, we've got to factor the top and the bottom so we can cancel the factors that are causing the 0 over 0 behavior, right? Indeterminacy. Okay? Let's try another one. Okay, what about this guy? What if I want to take the limit of f of x as x approaches 1/2?
1/2 or pi?
Or sorry, pi over 2.
Okay.
Yeah,
You just do the top.
just the top one, right? We're going to trade for the top function. Yep. We just take the limit of sine of 2x as x approaches pi halves, and I evaluate that directly. The sine of 2 times pi halves is the sine of pi. And what's the sine of pi? 0, right? Remember how that works. Unit circle. Remember how that works. On the unit circle, if I've got some angle theta, what are the coordinates of that point at theta? The x coordinate is what? Cosine or sine?
Sine.
Cosine. Goes alphabetically. C before s, x before y. So the x coordinate
That's fine.
is cosine theta, the y coordinate
Oh.
is sine theta. Right? And so pi is right there, isn't it? The coordinates of pi radians are -1, 0, and the sine of pi then would have to be the y coordinate, which is 0. Right? Is that ringing a bell?
I just went.
Yeah. Okay, don't do that though. Don't, you really want to use the unit circle. The unit circle is your best friend in trig. Everything comes from the unit circle. Okay, so what about this one? I want to take the limit of that rational function as x approaches -3. If I evaluate directly, what do I get?
X minus 2?
It doesn't work. You get 0.
How come? What do you get?
And then 0 over, wait,
Oh.
an indeterminate.
Indeterminate form, you get 0 over 0, right? 0 over 0 means more work. You can already tell what factors are going to have to cancel.
X plus 3.
As x approaches -3, what is it going to be again? X plus 3. I already know what's going to happen. I'm going to have x plus 3's cancel. I just have to finish the job. What else goes on the top? Oops, okay, good. These guys cancel algebraically, and now if I evaluate my limit directly, what do I get?
Negative 5.
Done. How about that? Sometimes people call that the dividing out technique. I don't know. I think it's kind of dorky to add that extra layer to it. It's just what you get when you simplify. But you know you are going to have to be able to divide out the offending factors. So it helps. You can kind of see what I'm trying to do for you guys here. I want you to be able to anticipate the strategy, not just like try to see at least a move ahead in calculus, and it really helps. You kind of know what has to happen. Now make it happen. And there's our notes for that. Okay. And they're there for you if you want to look at them. We don't need to. Okay, try one. Go to the book. Oh man, we don't have. I need to get some pens. Do a little
I will
bookwork
turn
here.
this classroom upside down.
back there.
Okay, I'll get pens
We
for
still
tomorrow.
have 3 groups. There's 3.
Okay, we do have some. That's fine.
And
Okay,
we're
go
small
for it.
class, it's just 3 per group.
Go for it. Yeah. Go 3 per group. Do this one real quick.
I need one over for that.
It's 5. Oh yeah, it's 5.
Okay, that looked pretty good. There were a couple things though, even people who got the right answer where they would have missed some points on a test. Let me show you what they are. Okay, this is kind of an important one. You can't omit the limit notation until you've actually evaluated the limit. So the next step is not to factor this stuff. Well, it is, but it's still inside a limit, right? So this would be the limit of x plus 3 times x plus 8 over x plus 3 as x approaches negative 3. Now technically, so I'll make this kind of grayed out, the next step would be, these cancel, would be the limit of x plus 8 as x approaches negative 3. But we can probably show that just by canceling those factors. So the next step that you would show then would be 5. You have to have that limit notation there though, because you haven't taken the limit yet. Okay? That makes sense. There's a big difference too, right? Limits are about approaching, expressions are about evaluating. Different. Okay? All right. Okay, what do you do here? Complex fractions are just fractions divided by fractions. So, what are you going to do? I mean, you kind of can make a prediction. What's going to eventually have to cancel?
The X.
X, right? X is the factor whose 0 is at 0. So, eventually X's are going to have to cancel. So what could you do? Well, one possibility is you just crank through some algebra. So we simplify everything on top, all this stuff. And what do I do to simplify that? How do I add fractions?
Common denominator.
Common denominators. What's my common denominator going to be?
10.
10.
Oh, 10.
Okay, 10 times the quantity x plus 10, right? How come?
You have to multiply it to get
They ain't
to.
got no
Exactly,
common
yeah.
thingies.
We know the least common denominator is going to be the least common multiple of the denominators. Well, the least common multiple of the denominators is going to be their product in this case, right? So we know we're going to get on the top, we're going to have to multiply this one by 10 over 10. So I'm going to get 10 over 10 times the quantity x plus 10 minus, multiply this one by x plus 10 over x plus 10. And what did I do wrong here? I made the same mistake. There you go. I made the same mistake I told you not to make.
Beginner calculus. Sorry.
And then on the bottom, we've just got an x, right, as x approaches 0. Okay, well, I can push those fractions together. And I get on the top then a common denominator of 10 divided by x plus 10. What do I get in the numerator? Right, I got a common denominator, and in the numerator, I should get all of this stuff. Right? So 10
But it's
minus
10.
the quantity x plus 10, which reduces to what?
X.
Not x,
Negative
Oh.
x.
negative
20.
x, okay?
Technicalities.
I've had enough.
We had enough.
So then I get the limit of, on the top, negative x over the quantity 10 times quantity x plus 10 divided by. So all this stuff is really grouped together, right? And if I divide a complex fraction by a complex fraction, I just multiply by the reciprocal of the denominator, just flip and multiply, right? So this all just becomes the limit of negative x over 10 times the quantity x plus 10 times 1 over x. Hey, look what happens. Just what you predicted. What cancels?
The X.
The x's. What do you know? Look at that. The x's cancel, and now I can evaluate this. As x goes to 0, look what happens. This guy, here's a good way to show that. Arrow 0. That goes to 0. What am I left with? Well, negative 1 on the top. On the bottom, I've got 10 times the quantity 0 plus 10. So I get negative 1/100.
Wait, why does the X on the denominator disappear?
Because we did two things at once. We canceled those x's, and then we took our limit. As x approaches 0, we'll just evaluate directly.
Okay.
Okay, make sense? Okay? All right, that's a good way to do it. Okay, there's an easier way. An easier way. Algebraically easier. Okay, it's easier just to clear all the fractions. Okay, you guys can tell me right away, what's the LCD on the top going to be? 10 times quantity x plus 10. You already told me last time, right? Okay, so what we can do here then is we can just, well, I won't do that. We're just going to distribute that through on the top and the bottom of this fraction. We're going to multiply essentially by that divided by itself. Okay, so okay, what happens? What happens when I distribute this thing to that term? What cancels? X plus 10, everybody agree? Everybody see that? So that's going to give me, in the top, when I do that distribution, I just get 10. Minus, what's going to happen when I do that distribution? What's going to cancel? The 10s, right? And I'm going to get minus the quantity x plus 10. And on the bottom, I just multiply straight across. And I just get 10x times x plus 10, right?
It feels a bit. I don't like it.
No, I agree. Okay, make sense? And that's right where we were before, isn't it? if I just simplify the top then, we get the limit of negative x over 10x times the quantity x plus 10. So we can do our vertical cancellation of those factors. Now this time let's not combine steps, let's include that extra step. Equals the limit of negative 1 over 10 times the quantity x plus 10 as x approaches 0. So that term is approaching 0, and I just get negative 1 over 100. That's quicker though, isn't it? A lot less algebra. You don't have to deal with common denominators. Clearing fractions is more efficient. Okay, so go do one. Use the efficient method. Clear the fractions.
Sorry, I can't see them.
So-
Cancels out.
Right? Everything looked great. You guys all figured out the LCD, and you're going to distribute that to the top and the bottom, right? So when we distribute to the top, we just get that big fraction. Right? I get 5 times the quantity x plus 9 over x plus 9. So look what happens. The x plus 9's cancel. When I distribute to the other fraction, I get 5 times the quantity x plus 9 over 5. So good. We cleared the fractions. So what's that give us then? Now we've got, on the top, I've got the limit of 5 minus the quantity x plus 9 divided by, on the bottom, that big old mess. 5 times the quantity x plus 4 times the quantity x plus 9 as x approaches negative 4. Well, on the top, what do I get? I get the limit of negative x minus 4 over the bottom. I could factor out a negative, right? Which is the same as the limit of negative the quantity x plus 4. On the bottom, I've got all that stuff. 5 times the quantity x plus 4 times the quantity x plus 9. Well, look what happens. As x approaches negative 4, you could have told me this. What has to cancel? X plus 4 over x plus 4. That's what was causing 0 over 0. So when those go away, now we can just take our limit. As x approaches negative 4, what are we going to get? Well, that's gone. On the top, only thing that's left is that negative 1. On the bottom, I've got 5 times x plus 9, but if x is going to negative 4, isn't that just 5 times 5? Negative 1/25. Right? Good, good?
We got it, guys.